Hello. Thank you for coming for this presentation. My name is Al-Tahir, presenting with Travis Barran our work on using the Unmanned Aerial Vehicle for earthwork calculations. Unmanned aerial vehicles are aircrafts that operate without a pilot on board, as from the name. Navigates manually or fully autonomous or in between. People refer to them different names for different historical reasons. The most common ones are the drone or UAV, or more recently UAS. That's because as a system containing more than just a vehicle. The interest with the UAV started a long time ago, basically for military applications and training. Only in the last two and a half decades, people had more growing interest in the UAVs for civilian applications. Actually, the production of the UAV themselves more than doubled in the last 2 decades. The main reason for that interest is enhanced performance. Now they have smaller and more efficient GPS and gyroscopes and cameras. And also there is more sophisticated algorithms for processing the images, so layman people can get the outcome without too much training. Other reasons for the popularity of the UAV, it's a cost-effective, almost in every application. Besides, it's portable and quick deployment. Take it, put it in the car, move around, set it up and fly it again. And can be used in very high-risk situations and inaccessible areas. As relevant to this study, it's minimized the disruption of working site. You don't need to stop the trucks to do your measurements. You don't need to wait for them to stop to do your measurements, and reduce the chance for site accidents on the surveyors and other workers. Other applications for other civilian applications for UAVs, search and rescue, one of the famous applications, policing and monitoring, controlling traffic, second largest application of the UAVs. More relevant to natural resources is mining, forestry, infrastructures, especially for power lines, disaster management, not so scientific applications, filming weddings, delivery of medical, now it's getting there, and other material, and sport. Back to our topic here. Obtaining volumetric data for earthwork is a very important task for many of the civil engineering applications, especially highways, constructions, other applications, mining, and other things. The way they deal with it now, you take a measurement on the surface, you add another layer or remove some mining, and then take a measurement of the second surface, and you subtract the two surfaces, you get your volume, typically using total stations or global positioning systems. And as you would expect, this is more labor-intensive, time-consuming, and putting the surveyors in danger, working between the machinery, heavy machinery. So what we're promoting here and proposing is the use of UAVs for doing that task. And we'll be evaluating its performance against the total stations in terms of accuracies, cost, and timing. So we chose a small area, active site on the extension of the highway, on the Churchill Roosevelt Highway extension, and it's about 80 meters length with about 20 meters width. And you can see the site here. where it's at the subgrade level. This is the starting point where they have the subgrade already done. We flew our first mission, took pictures for the surface, and then they put the sub-base material compacted, and we flew our second flight mission. And the idea that we compare the volumes between the two surfaces. Of course, the project went the normal procedure, went to the site visit, we evaluated the danger and the safety and availability of tree lines as affecting our flight, and we designed our flight. Meanwhile, we collected the ground control points around the section, and we flew the UAV and took several images. In the first mission, we flew more than what we need, so collected more 160 points, although we used about 160 photographs, although we used about 50 photographs for the process. And then we decided to cut down the number of photos, and the second mission took only about 34 images. We took the photographs, we put them in the software, we used edgy software, very commercial and mainstream software, and the software went through the whole process of orientation and then aerial triangulation, and then finally produced a dense set of three-dimensional points, millions of them for each mission, about 4 million to 20 million, that's plenty. We changed the setting. So after that, we should create the two surfaces to compare to get the volume. So we use the points that are collected from total station, and that's over the same section. At the subgrade level, we collected slightly more points than on the sub-base level. That's about 10 meters up distance between these points. We use the triangular irregular network method. That's a tin, and we generated surfaces, digital surfaces from there, and we subtract one from the other one. We use the UAV image data, the points that we collected from the UAV, and couldn't use the millions, so we filtered them down to about 120,000. That gave us about 15 centimeters between every point. And that's going to give us, it's about 4,000 points instead of in every of these between 4 total station points. So that will give you the amount of data that we get from there. So now let's do our analysis, evaluation of the accuracies. Our input was ground control points using GPS. The result, the accuracy were about 2 centimeters or 3 centimeters in X and Y, and less than 1 centimeter in Z. So that will tell you that that's the starting point. We started with 2 centimeters accuracies in X and Y. Those control points were same accuracy applied to the total station points, and then these control points were input into the aerial orientation of the aerial photographs. So first evaluation was to see whether our total stations versus the interpolated surfaces as a point. So we took these 27 and 25 points collected by total station, compared their values with their values on the interpolated relevant surface from the UAV. And we end up about 4 centimeters average error. Well, that's very good within the expectation of the project. Then we compared the volumes difference between subtracting the two surfaces generated by the UAV and the two surfaces generated by the total station gave us 680 cubic meter, while the surfaces from the UAV gave us 740 something, and the difference around 63 cubic meter, or less than 10% difference. Now, our explanation for that difference is that having 4,000 points instead of 4 points in every square here will give you a better representation of the actual surface of reality. And all smaller variation and the surface here between these points will be captured by the UAV data. So our conclusion here in this task, that you get a better and more accurate and more realistic representation of reality, and the volume here should be more representative of reality. Then we compared the time. It was not that big difference between them in the field, being about 80 meters. The difference was in the processing of the data, and we should expect with the aerial photography, we have more time to process the data, and then we have more points from the UAV to process compared to the total station. So there was a big difference in time. The UAV took longer time to process. However, our observation here, we would like to mention here that in the data collection part, if you have a larger site, which typically you do, then the difference, you will take longer time to do the total station field work. And that will be more gaining for the UAV here. In terms of the processing here, of course, we can reduce the number of points used by the UAV, as well as at the end, we're still having a better representation, more dense representation of the surface. So what you gain from the extra time, you get more accurate results. And finally, we compared the cost. We didn't compare it per project, but we used the purchasing cost as an indicator for the difference here. And you can see here the purchasing cost for the total stations and all accessories is around 60-something thousand US dollars, while for the UAV and the processing software is around 30,000 US dollars. And that's already 50% saving on the cost. If you want to prorate it over a project, and then we still have the same difference. So in conclusion, we proved that the UAV is more appropriate, more cost-effective, and time-saving to do earthwork measurements for earthwork calculations. We achieved the accuracy within the project specification. They were asking for 5 millimeters, and we get 4 millimeters. We proved also that the UAV is more accurate in presenting the reality of the surface, and we, as such, will be more accurate of representing the actual volume. We saved on the cost by purchasing cost and of the operation, and then we expect we'll be saving on the time for field work. Thank you very much. I will be happy to answer your questions, or you can email me at this address. Have a good day.